Okay, let's solve this exponential equation. And what makes this situation different than the previous is that we'll have these two numbers sitting in front now. And if you look before that, we didn't have that situation. And you have exponents on both sides. So what can we do? Again, our job is to bring this exponent down, right? This variable exponent down. And the only way to do that is through log rules. And I need to separate these two in order to accomplish it. So the log rule I want to use is this one. It says log of a to the x, and this could be written as x log a, like so. But if you look closely, there is just some expression raised to that power. The 9 is not being raised to x, only the 1.07. So I have the situation. What can I do? Well, I have another rule that says if I'm multiplying two things, which I am, I can always separate it, but again, taking the same thing when I take the log. So all of a sudden, I can separate the two, the product here, by adding logs. So that's what I'm going to do first. I'm going to just take the log of both sides. I'm going to just choose the natural log. No particular reason why. The natural log, except it's just nice. And I'm going to take log of the other side. So I take the log of both sides. Now I can apply this rule and separate this product. So I'm applying the, the log of a product there inside the log. And how does that help me? Well, notice now I can apply the second rule, which would bring that down. So if I can do that right now. Like so. Now, I don't know if you're aware, but what I have here is just a linear equation. That's all. I have my variable times n number. Oops, I didn't write that right. Still have that x up there. Brought it down. So it's just some number times x plus another number. It's linear, same thing. The variable times some number plus some number. Again, so if I'm solving a linear equation, I bring all the items, all the terms that have the variable to one side, all the constants to the other side. So I'm going to subtract natural log of 12 from both sides. And I'm going to subtract x times the natural log of 1.07 from both sides. And again, like I said, this is a linear equation. If this had been a number like 5 and this been 7, I just subtracted 7 minus 5 is 2. But I cannot subtract these two numbers. I'm not sure what they are. So in order for me to continue, I need just one instance of x. And to create that, I'm going to factor x out. And now I can divide both sides by this to get the other side. Now, this is optional, but just to show you that we can, the whole point of this is to condense when we have to apply the log rules. So if I apply now the other log rule, that says when I have a difference of logs, I can write them as a ratio. Right, so then I can come over here and write this as natural log of 9 divided by 12. Um, and here I can do the same thing. I'll do it just to clean this up a little bit before I cannot really reduce that any further, not in my head. But then I'll divide both sides by this natural log of 104 over 107. And there's my exact answer. Now, is this the answer to this question? Well, one thing I do notice that these are exponential, so the domain of this is negative infinity to infinity, and the domain of this is negative infinity to infinity. So this should work. Let's try it and see what it looks like on Desmos. I'm going to type this into Desmos. I got 9 times 1.07, and all raised, and of course this is so I've got natural log and 9/12. We're going to reduce that down, but I'm not clicking right now. Divide that. Right, there you go. Divide that by natural log of 1.04 divided by 0.07. And that looks right. It's a mess, but I get that number. Fantastic. Now I'll do the other side, and it should come up to exactly the same number, 12 times 1.04. And I'm going to just cheat here and grab this. And there we go. It comes out exactly the same. So indeed, this is a solution. So we found indeed the solution. And notice again, this was the exact answer. If we enter this into a calculator like we just did, all we get is an approximation. We saw that the two were equal to the number of decimal places that this thing produced. There you have it.